Right now, without a sound, without the faintest sensation, something older than the first star is passing through the palm of your hand. Not a memory of it, not a picture of it. The thing itself, a particle that stopped touching the rest of the universe when the cosmos was 1 second old, and hundreds more like it are crossing every fingertip you have. This second, and not one of them will ever touch you. We are taught that the beginning of the universe is the most distant thing there is, sealed away behind nearly 14 billion years. But here is what that story leaves out. A handful of things were forged in the first instant, some of them before ordinary matter even existed, and they never left. They are still here. One of them may be drifting past Neptune right now, older than the Sun, the size of a piece of fruit and heavier than the Earth. The beginning did not end. It is in the room with you, so get comfortable and settle in. If you're new here, hit subscribe and stay a while, because by the end of tonight the words "the beginning of the universe" will no longer feel like something far behind you, but something quietly passing through your open hand in the dark. Now, let's slowly ease into this. Part 1. The beginning, we were told, had no before. There is a version of the story you have almost certainly heard, and it is a comfortable one. It goes like this. In the beginning, there was a single moment, and before that moment there was nothing at all. No space, no time, no matter, no place for a question like before to even land. Everything that exists, everything you have ever seen or touched or been, was made in that first instant and in the long, slow cooling that followed. The universe, in this telling, has no attic and no keepsakes. It has no objects older than itself, because there was no self to be older than, and no shelf on which anything ancient could sit and wait. This is the picture most of us carry to sleep, and it is a tidy one. It draws a clean line at the bottom of time and says, "Here, this is the floor. Do not look underneath it. There is no underneath." And for a long while that felt like the honest thing to say, because the mathematics we used to describe the early universe genuinely broke down as we ran the clock backward. Everything grew hotter and denser the further back we went, until, at the very first instant, the equations returned numbers that meant nothing, infinities where there should have been temperatures and densities. When your best description of reality hands you an infinity, it is usually a polite way of admitting that your description has stopped working. So we drew the line, and we called it the beginning, and we let it be the edge of the map. Tonight I want to walk you very slowly toward that line, and then gently I want to step over it. Because the more carefully physicists have looked at the earliest moments, the more the tidy story has come apart in two directions at once, and both of them are stranger and, I think, more beautiful than the version with the clean floor. The first direction is backward. It turns out that the hot, dense fireball we casually call the Big Bang was almost certainly not the true first act. Something came before the fire. We will get to what that something was, and it is not a comforting fairy tale but a serious testable idea that most cosmologists now take as their starting point. For now, I only want to plant the thought, quietly, that the word "before" may not be forbidden after all, that the beginning we were handed might itself have had a beginning. The second direction is stranger still, and it is the one this whole video is built around. It is the discovery that a small number of things made in the universe's very first moments never went away. They did not get folded into stars or burned into new elements or lost to the long expansion of space. They survived. They are still here, tonight, drifting through the dark and in at least one case drifting through you as you lie there listening. The universe, it turns out, does have an attic. It kept a few things, and some of those things are older than the first star, older than the first atom, older, in the most literal sense, than light itself. I want you to sit with how odd that is. We are used to thinking of the beginning of the universe as the most distant possible thing, unreachable, sealed off by nearly 14 billion years, and yet a piece of it may be passing through your hand right now, and another piece may be quietly orbiting our own sun, out past the last planet, in the cold. The oldest things in existence are not only far away in time, some of them are also impossibly close. To find them, though, we have to understand what old even means when we're talking about the universe, and we have to be honest about what we know and what we only suspect. So let me begin the way the universe began, with a number so small it barely deserves the name, and then let me show you why that number hides a door that the tidy story told us was a wall, Consider what we can actually see when we look back in time, because in astronomy, looking far away is the same thing as looking into the past. When you look at the moon, you see it as it was a little over 1 second ago, because that is how long its light took to reach you. When you look at the sun, you are seeing light that left it about 8 minutes ago, and when the largest telescopes look at the faint smudges at the limit of their vision, they are seeing light that has been travelling for more than 13 billion years, light that left before the Earth existed, before the sun existed, when the universe was young. Every time you look outward, you look backward. The night sky is not a picture of how things are. It is a picture of how things were, layered, each object showing you a different depth of the past all at once. This single fact, that distance is time, is the thread that will run through everything tonight, so hold on to it. It means that the further out we push our instruments, the closer we creep toward the beginning. And it means that the beginning is not simply gone. Its light, its particles, its imprints are still arriving. The past is not behind us in the way a closed door is behind us. The past is around us, streaming inward from every direction, at the speed of light, forever. It is worth remembering that the idea of a beginning at all was, not so long ago, deeply unwelcome to many scientists. For a long stretch of the 20th century, a great many thoughtful people preferred to believe the universe had always existed, unchanging on the larger scales, with no origin to explain, because a universe that simply always was seemed to raise fewer awkward questions than a universe that began. When the evidence first arrived that the universe is expanding, that the galaxies are all rushing apart, and that running the expansion backward implies they were once packed together in a hot, dense state, the implication was resisted, sometimes fiercely. The very phrase Big Bang was coined, by one of the idea's critics, as a term of mockery, a dismissive nickname for a theory he found faintly absurd. The name stuck, ironically, long after the evidence had turned decisively in its favour. What convinced people, in the end, was not argument but measurement, the expansion of the galaxies, the abundance of the light elements, and above all the ancient background light we will visit shortly, all pointing to the same hot, dense past. The beginning was not a philosophical preference. It was forced on us by the sky. I mention this history because it is a useful reminder as we go further tonight. The scientists who resisted a beginning were not foolish. They were reasonably cautious about a claim that seemed to overreach the evidence, and they held out until the evidence became overwhelming. That same caution is exactly what we owe the stranger claims ahead, the relics from before matter, the black hole that might orbit our sun. We will hold each of them to the same standard the beginning itself had to meet. Some of them clear that bar cleanly, some are still reaching for it, and part of the pleasure of this subject is learning to tell, calmly, which is which. For most of the 20th century, the furthest back we could see was a wall. It sits at about 380,000 years after the beginning, and we will visit it properly later, because it is one of the relics, the oldest light there is. But a wall implies something behind it, and the entire adventure of modern cosmology has been the slow, patient effort to figure out what is on the other side of that wall, in the first seconds, the first fractions of a second, and finally in the strange moments that may have come before the fire ever lit. So this is where we begin. Not at the beginning exactly, but at the comfortable story about the beginning, the one with the clean floor and the empty attic. Keep it in your mind, because we are going to take it apart very gently, one piece at a time, and the first piece to go is the idea that the fireball was the first thing that ever happened. Because before the universe was hot, before it was a roaring furnace of light and matter, the evidence suggests it was something else entirely. It was cold and empty, and it was expanding at a rate that should be impossible. What happened in that instant did not just start the universe. It set the stage for every relic we're about to hunt, and it is where we are going next. Part 2. The fire had a before. Let me tell you what most cosmologists now believe happened before the fireball, because it is the reason the word before is allowed at all. The idea is called cosmic inflation, and at first it sounds like a small technical adjustment. It is not. It is a claim that the universe, in its earliest instant, did something so violent and so brief that it almost defies the meaning of the words we use for time. Here is the picture. Before the universe was a hot, dense soup of particles, it was dominated by a kind of field, an invisible something filling all of space, carrying an enormous amount of energy simply by existing. Physicists call the thing driving this the inflaton, and you can think of a field, loosely, as a condition of space itself, a value that exists at every point, the way temperature or pressure exists at every point in a room. This particular field had a strange property. Its energy did not dilute as space grew, and that meant the more space expanded, the more total energy there was to drive still more expansion in a runaway that fed on itself. The result was an expansion unlike anything that has happened since. In a sliver of time so short it is hard to write in ordinary words, the universe doubled in size and doubled again and again, over and over, dozens of times. To give you the numbers, this happened in the window between roughly 10 to the minus 36th of a second and 10 to the minus 32nd of a second after the clock started. Those are not typos, and they are not poetry. 10 to the minus 36th of a second is a decimal point, followed by 35 zeros, and then a 1, a portion of a second so small that the fastest processes we can measure in a laboratory are, by comparison, geological. And in that impossibly brief window, a region far smaller than a single proton was stretched to something like the size of a grapefruit, or larger. An expansion that, if you tried to picture it at human scale, would take a grain of sand and blow it up to span galaxies in less time than it takes anything to happen. Then it stopped. The field driving the runaway ran out of the peculiar condition that let it push, and it did what a wound-up thing does when it is released. It began to oscillate, to slosh back and forth around its resting value, and as it did, it poured its enormous stored energy into a flood of ordinary particles and radiation. This is the moment the fire actually lit. Physicists call it reheating, and it is, in a very real sense, the true birth of the hot Big Bang, the furnace, the roaring plasma of light and matter that everyone pictures when they hear the phrase. The fireball was not the first thing. The fireball was what inflation left behind when it ended. I want you to notice what has just happened to the story. The single, tidy first moment has split in two. There is the hot Big Bang, the fireball, which is real and which we have mountains of evidence for. And there is something before it, a phase of pure, cold, exponential expansion that set everything up and then handed off to the fire. When people say, before the Big Bang, this is the honest thing they can mean. Not a fantasy, not a mystical void, but a physical process described by mathematics that preceded the furnace and lit it. The fire had a before. Hold on to that phrase because we will come back to it near the end when we go looking for the one relic that might carry a message from that side of the flame. I should admit before going on that we do not know what the inflaton actually was. We have a role that needs filling, a field with the right properties to drive the expansion and then decay into the fire, but we do not yet know its identity, the way we know the identity of, say, the particle that gives things mass. There are many candidate ideas, and sorting between them is part of why the hunt for the faint imprints of inflation matters so much, because those imprints would tell us about the field that made them. So when I describe the inflaton, I am describing a part in a play whose actor has not yet been named. This is not a weakness in the story so much as an honest edge of it, the place where confirmed physics shades into active research. The expansion is strongly supported by evidence. The precise nature of the thing that drove it is still being worked out. Both of those can be true at once, and holding them together is exactly the calm, careful attitude this subject rewards. Now, you might reasonably ask why anyone believes any of this. It is a wild claim, an invisible field driving an impossible expansion in a time too short to name. Why would a careful scientist accept it? The answer is that inflation was not invented to be dramatic. It was invented to solve problems, and it solved them almost too well. The universe we see has some features that, without inflation, are deeply suspicious. It is astonishingly uniform. When we look at that ancient wall of light I mentioned, the oldest light there is, and we measure its temperature in one direction of the sky, and then measure it in the exact opposite direction, the two match to within a tiny fraction of a degree. That should be impossible, because those two patches of sky, in the standard story, were never in contact. They sit on opposite sides of the observable universe, too far apart for any signal, even light, to have crossed between them in the time available. So how did they agree on a temperature? It is like meeting two strangers from opposite ends of the earth who have never communicated and finding they are wearing the identical outfit down to the thread. Either it is an outrageous coincidence, or they were once much closer together than they appear. Inflation gives you the second answer. If the entire visible universe grew from a region far smaller than a proton, then all of it was once in intimate contact, close enough to reach a common temperature before inflation blew it apart to enormous size in an instant. The uniformity is not a coincidence. It is a memory of a time when everything now spread across the sky was packed into a single tiny well-mixed speck, and inflation does something even more remarkable. The tiny quantum jitters in that original speck, the unavoidable flickering that the laws of the very small impose on any field, got stretched along with everything else, frozen into the fabric of space as faint ripples of slightly more and slightly less. Those ripples became the seeds. Every galaxy, every cluster, every string of light across the modern sky grew from those stretched-out quantum flickers. The largest structures in existence are the fossils of the smallest possible fluctuations, magnified by the most violent expansion there ever was. The uniformity is not the only riddle inflation quietly solves either. There is a second one, just as strange, having to do with the overall shape of space. When we measure the geometry of the universe on the larger scales, we find it is astonishingly flat, meaning that parallel lines stay parallel, and the angles of a cosmic triangle add up just as they would on a flat tabletop, rather than curving as they would on the surface of a sphere or a saddle. This sounds unremarkable until you realize how delicately balanced it has to be. In the ordinary picture, a universe that starts even slightly curved grows more curved over time, the deviation amplifying as the universe evolves. So for space to look this flat now, it would have had to begin flat to an almost impossible precision, balanced on a knife edge for 14 billion years. That kind of fine balance with no reason behind it is exactly the sort of thing physicists distrust, and inflation dissolves it effortlessly. If you take any curved surface and stretch it enormously, it looks flat, the way the ground beneath your feet looks flat even though the earth is round, simply because you are seeing a tiny patch of a hugely magnified whole. Inflation stretched the universe so violently that whatever shape it started with, the part we can see was flattened smooth. Two separate puzzles, the impossible uniformity and the impossible flatness, both fall to the same single idea. So this is not a small technical footnote. Inflation reframes the entire origin. It says the fireball was a second act, that a colder and stranger phase came first, and that the imprint of that phase is written across the whole sky, in the uniformity and in the seeds of structure. It gives the word before a physical meaning, and it opens the door we need, because if there was a before, then there can be relics from it, or from the very edge of it, survivors from the first instant that carry the origin forward into the present. What exactly counts as such a survivor, and why almost nothing qualifies, is the next thing we have to understand. Because the universe made a great many things in its first moments, and it destroyed almost all of them. Only a precious few slipped through. Those few are what we are hunting. Part 3. What a relic really is. We need to be careful with the word relic, because it is going to carry a lot of weight tonight. In everyday speech, a relic is an old object, something that has survived from a distant time, a bone in the ground, a coin in a field, a tool left by hands that turned to dust long ago. What makes a relic precious is not only its age, it is the improbability of its survival. For every relic that reaches us, countless other things from the same era were lost, decayed, buried, burned, erased. The relic is the exception, the one piece that slipped through a gauntlet of destruction and arrived somehow intact. The universe is the same, only far more ruthless. The early cosmos was not a gentle place where things could sit undisturbed. It was a furnace, then a fog, then a slow churning of collapse and ignition as the first structures formed. Almost everything the young universe made was unmade. Particles were created and destroyed by the trillions of trillions every instant. Matter and antimatter met and annihilated, leaving only the faint surplus that became everything we see. The temperatures were high enough to tear apart any structure the moment it formed. If you are looking for something that survived from the first second, you are looking for a survivor of the most hostile conditions that have ever existed anywhere. So the question becomes very sharp. What could possibly last? What kind of thing could be forged in that first second and still be here, unchanged in its essence nearly 14 billion years later? The answer turns out to be a very short list, and every item on it is strange, and every item on it is a character in tonight's story. The first way to survive is to stop interacting. If a particle simply refuses to touch anything, if it slips through matter as though matter were not there, then nothing can destroy it, because destruction requires interaction. There is a kind of particle that does almost exactly this, and it decoupled from the rest of the universe when the cosmos was about 1 second old, and it has been flying free ever since, untouched and untouchable. It is the oldest surviving thing we can, in principle, detect, and there are hundreds of them in every sugar cube of space around you, and we will meet them in 2 parts time. The second way to survive is to become so extreme that the ordinary rules of destruction no longer apply to you. If matter falls together tightly enough, gravity can seal it off from the rest of reality entirely, wrapping it in a one-way surface from which nothing returns. We call the result a black hole, and while you have surely heard of black holes formed from dying stars, there were no stars in the first second. And yet, some physicists argue, the conditions in that first instant may have been extreme enough to make black holes anyway, directly, out of the raw density of the young universe, before a single star had ever shone. Those would be the oldest objects there are. They would predate matter itself, and they are the central figure of everything we are building toward tonight. The third way to survive is to be a ripple in the fabric of space rather than a thing within it. If the violent processes of the first instant sent waves through space-time itself, those waves would still be passing, faint almost beyond measure, carrying information from before the fire. This is the rarest and most precious potential relic of all, and it is the one that might reach back past the fireball into inflation itself. We will end there. There is a quiet symmetry in these 3 escape routes that is worth pausing on. Each one is a different way of refusing to be part of the ordinary give and take that destroys everything else. The neutrino refuses by not touching. The black hole refuses by sealing itself away behind a surface nothing can cross. The tremor in space refuses by not being a thing at all, only a passing shape in the fabric that carries no material to be broken. 3 refusals, 3 loopholes, 3 ways of slipping out of the flow of destruction that recycled everything ordinary. And notice that each one reaches back a little further than the last, the neutrinos to 1 second, the black holes to before matter, the tremors to before the fire, as though the deeper you go toward the beginning, the stranger and more extreme a thing has to be to have survived the trip. The relics are not just old, they are arranged roughly, in order of how impossible their survival was, and the oldest are the most impossible of all. Notice the pattern. To survive from the beginning, a thing has to be exceptional in one of a few specific ways. It has to refuse to interact, or it has to be sealed off by gravity, or it has to be a tremor in space rather than an object at all. Everything ordinary, everything made of the atoms you know, everything that touches and reacts and burns, was recycled long ago. The relics are the strange ones. They are the things that found a loophole in destruction. Let me put the ruthlessness of that recycling in the plainest possible terms, because it is what makes the survivors precious. Almost every particle in your body has been remade, over and over, since the beginning. The specific protons and neutrons in your atoms did form early, in the first minutes, but they have spent the intervening eons inside stars, cooked and fused and scattered and gathered again, folded into worlds and torn apart and folded once more. The matter you're made of is ancient in its ingredients, but endlessly reprocessed in its arrangement, like a house built and rebuilt so many times from the same bricks that nothing of the original structure remains. That is the fate of ordinary matter. It endures, but only by being constantly transformed, so that it carries no clean memory of the beginning. It is a bucket of very old bricks with no trace left of the first wall they were laid in. The relics are different precisely because they were never rebuilt. The relic neutrino that passes through your hand tonight has not been inside a star. It has not been fused or scattered or gathered. It has done nothing at all since the first second except fly in a straight line through the growing dark. The primordial black hole, if it exists, has not been remade either, only slowly bled at its edge, its interior a sealed and untouched pocket of the first instant. This is the real meaning of a relic. It is not merely old, it is unchanged. It carries the beginning not in reprocessed fragments, but in its original unaltered form. To meet one is not to meet a descendant of the origin. It is to meet the origin itself, still here exactly as it was. This is why the relics matter so much beyond their age. They are the only direct physical connection we have to the origin. Everything else we know about the beginning is reconstruction, inference, running the equations backward and trusting the mathematics. But a relic is not a reconstruction. A relic is a piece of the thing itself, arriving in the present, available to be measured. If you could hold one, you would be holding the beginning in your hand. And the recurring quiet astonishment of this whole subject is that in at least one case, you very nearly can. The relic is passing through your hand already. You simply cannot feel it. I keep returning to that idea because it is the emotional core of what makes this topic different from an ordinary lesson about the early universe. This is not a story about something that happened long ago and far away and is now safely finished. This is a story about something that never finished, that never left, that is still here, threaded through the present, moving through the room you're lying in. The title of tonight's video is not a metaphor. Something ancient really was here before the fire, and it really never left, and by the end I want you to feel the full, strange weight of how true that is. But to feel it, we have to build up to it slowly, the way the universe itself was built up, layer by layer, from the first fraction of a second outward. So before we reach the black holes forged before matter, and before we reach the particles passing through your hand, we should visit the most famous relic of all, the one we can actually see, the oldest light in existence. It is the wall at the edge of time, and it is a photograph of the universe when it was still an infant. It is not the oldest relic, as we will discover, but it is the one that taught us relics were possible at all. That wall of ancient light is where we go next. Part 4. The oldest light in existence. For most of the history of science, if you had asked how far back we could actually see, the answer would have been a kind of wall. Not a wall of brick or stone, but a wall of fog, and beyond it, nothing our eyes or instruments could ever reach. That wall is real, and it surrounds us in every direction, and the light coming off it is the oldest light there is. To understand the relics we cannot see, it helps to start with the one we can, because it taught us that the beginning left traces at all. To find the wall, we have to go back to a time when the universe was very young and very hot, about 380,000 years after the beginning. That sounds like a long time, but against the nearly 14 billion years the universe has lived, 380,000 years is less than a blink. It is the equivalent of the first few hours in the life of someone who lives to be 100, and in those first few hours the universe was a place where light could not travel freely at all. The reason is worth sitting with, because it explains the wall. In the early universe, everything was so hot that atoms could not hold together. An atom is a nucleus with electrons bound around it, but at temperatures of thousands of degrees, the electrons are torn loose, and everything exists as a charged soup, nuclei in one place, electrons roaming free, and light does not pass through a charged soup like that. Charged particles grab photons, scatter them, throw them in random directions, so that any beam of light trying to cross the young universe would be knocked sideways again and again, taking a stumbling, staggering path that went nowhere. The universe was not dark, it was blindingly bright everywhere, but it was opaque, a glowing fog in which light could not get anywhere, like the inside of the sun or the inside of a cloud lit from within. Then the universe cooled, and at about 380,000 years it crossed a threshold. It became cool enough, finally, for the electrons to settle into orbits around the nuclei and form the first neutral, complete atoms. And the moment that happened, the fog cleared. The charged soup became a transparent gas, and all the light that had been trapped, scattering endlessly, was suddenly free to fly in a straight line, forever. That flash of release, the instant the universe became transparent, sent light streaming out in every direction. And that light is still travelling. It is still arriving. We call it the cosmic microwave background, and it is the oldest light in the universe, a snapshot of the moment the fog lifted 380,000 years into the story. Take a breath and picture what that means. In every direction you could point, if you had the right kind of eyes, you would see a faint, even glow, the same everywhere, filling the whole sky. It is not the light of any star or galaxy. It is the light of the young universe itself, the afterglow of the fog clearing, arriving from a time before there were stars to shine. When you turn on an old television set tuned to no channel and see that flickering static, a small fraction of that hiss, historically, was this ancient light, the microwave background caught by the antenna. The beginning of the universe was, quietly, playing on your television. We have now mapped this ancient light with extraordinary care, with satellites that spent years staring at it, and what they found confirmed the story we have been telling. The light is almost perfectly uniform, the same temperature across the whole sky, which is the uniformity that inflation was invented to explain. But it is not perfectly uniform. There are faint patches, slightly warmer and slightly cooler, differences of a few parts in 100,000, and those patches are the seeds we talked about, the stretched-out quantum flickers from inflation, frozen into the young universe and revealed in this light. When we look at the microwave background, we are looking at the map of where every future galaxy would eventually grow. It is a baby photograph of the cosmos, taken when it was hours old and printed across the entire sky. So the microwave background is a relic. It is genuinely ancient, genuinely a survivor from the young universe, genuinely still here and still arriving. It taught us that the beginning was not sealed off, that its traces reach the present, that we can point an instrument at the sky and measure something made when the universe was an infant. In every popular telling, this is where the story of cosmic relics both begins and ends. The oldest light, the baby photo, the edge of what we can see. But here is the quiet twist that reframes everything, and it is the reason we do not stop here tonight. The microwave background, for all its fame, is not the oldest relic. It is only the oldest one that happens to be made of light, and therefore the oldest one we can see. Remember the number. The light was released at 380,000 years. That is when the fog cleared for photons. But other things had already stopped interacting long before that, in the first second, when the universe was hundreds of thousands of years younger than this famous wall. Those things do not glow. They do not announce themselves. They are not a picture in the sky, but they are older, by a wide margin, than the oldest light. They decoupled from the universe when it was 1 second old, and they have been flying, silent and untouched ever since. It is worth pausing on how we found this ancient light, because the story is a small lesson in how the universe hands us its relics almost by accident. In the middle of the 1960s, 2 engineers at a laboratory in New Jersey were working with a large sensitive antenna, and they kept finding a faint hiss in their instrument, a background static that would not go away. It came from every direction of the sky, day and night, in every season, and no matter what they did, they could not get rid of it. They checked their equipment obsessively. They even climbed inside the antenna and cleaned out the droppings left by a pair of pigeons that had roosted there, suspecting the mess might be the source of the noise. But the hiss remained. What they did not know at first was that a group of physicists not far away had been predicting exactly this, a faint afterglow left over from the hot early universe, cooled by billions of years of expansion to just a few degrees above absolute zero. The 2 engineers had accidentally found the oldest light in existence while trying to eliminate it as noise. It was, in the most literal sense, the sound of the beginning, and they had been trying to clean it off their antenna. The discovery would eventually be recognized as one of the most important in the history of science, because it turned the early universe from a story into a measurement. Since then, we have studied this ancient light with extraordinary care, sending satellites above the atmosphere to map it across the entire sky, each one sharper than the last, until we knew its temperature to be about 2.7 degrees above absolute zero, uniform to a fraction of a degree, with the faint warmer and cooler patches picked out in exquisite detail. Every one of those maps confirmed the same thing, that we are surrounded in every direction by the cooled afterglow of the moment the fog lifted, and that within its faint unevenness lies the blueprint of everything that would ever form. The oldest light is not a metaphor and not an inference. It is a photograph, taken by the universe of itself, when it was a few hours old, and we have it framed on every wall of the sky. The wall of ancient light, in other words, is not the true edge of the past. It is only the edge of the visible past. There is an older layer, invisible, made not of light but of matter of the ghostliest kind, and it is passing through you right now, in numbers you would not believe. That older layer is where we go next, and once you understand it, the microwave background will look for the first time young, because there is something in this room that is older than the oldest light, and I am about to introduce you to it. Part 5. Older than light. I want to introduce you to a particle, and I want to do it slowly, because everything about it runs against your intuition, and the point is not to overwhelm you, but to let the strangeness settle in. The particle is called the neutrino, and it is one of the most abundant things in the universe, and it is also, from the point of view of ordinary matter, almost perfectly a ghost. Start with why it is a ghost. Everything you have ever touched, you touched because of electric forces. When your hand rests on a table, Your atoms and the table's atoms do not actually meet. Their electrons repel each other, and that repulsion is what you feel as solidity, as touch, as the table pushing back. Almost all of your experience of the physical world is this electric conversation between charged particles. The neutrino does not join that conversation. It carries no electric charge at all. It does not feel the electric force, does not push, does not repel, does not touch in the way anything you know touches. It responds only to gravity, which for something so light is almost nothing, and to a second force, the weak force, which operates only across distances smaller than an atomic nucleus and only very rarely. This makes the neutrino nearly unstoppable. It can pass through solid matter as though the matter were empty space, because for a neutrino it very nearly is. Let me give you the number that makes this vivid. A neutrino could pass through a wall of solid lead, and to have a fair chance of stopping it, that wall would need to be around a light year thick, not a mile, not 1,000 miles. A light year, the distance light travels in a year, of solid lead, and even then it is only a fair chance. The neutrinos streaming out of the sun pass through the entire Earth, all of it, the crust, the mantle, the molten core, and out the other side, as if the planet were a pane of clear glass, as if it were not there at all. Now hold that ghostliness in mind, because it is exactly what let the neutrino become a relic. Cast your thoughts back to the first second of the universe. Everything is a searing, dense plasma, everything crashing into everything, and neutrinos are part of that crowd, colliding and interacting like all the rest. But as the universe expands and cools, it thins out, and interactions grow rarer, and for a particle as reluctant to interact as a neutrino, a moment comes very early when it simply stops touching anything at all. That moment arrives when the universe is about 1 second old. From that instant the neutrinos decouple. They let go of the rest of matter and begin to fly free, and because they barely interact, nothing ever stops them again. They have been flying, in a straight line, untouched, for nearly 14 billion years. Do the arithmetic on that and feel it land. These neutrinos stopped interacting at 1 second. The famous microwave background, the oldest light, was not released until 380,000 years, which means these particles are older, as relics, than the oldest light by more than 300,000 years. They are a snapshot not of the universe at 380,000 years old, but of the universe at 1 second old. They are the oldest surviving thing we have any hope of detecting, and they are not rare, out at the edge of the universe. They are here. They fill all of space, cooled now to a temperature of just under 2 degrees above absolute zero, at a density of about 336 of them in every cubic centimetre. 336 ancient neutrinos in a volume the size of a sugar cube, everywhere, including the sugar cube of space at the centre of your chest. The story of how we even came to know this particle is worth telling, because it began as an act of near desperation. In the early part of the 20th century, physicists studying a certain kind of radioactive decay found that energy seemed to go missing. Before the decay, they could measure a certain amount of energy. After it, a little was always gone, unaccounted for, vanished. This was a genuine crisis, because the conservation of energy is one of the deepest commitments in all of physics, the principle that energy is never created or destroyed but only moved around. Rather than abandon that principle, a physicist named Wolfgang Pauli made a bold and reluctant proposal in 1930. He suggested that the missing energy was being carried off by a new, unseen particle, one with no charge and almost no mass, so ghostly that it slipped away from every detector unnoticed. He called it a desperate remedy and apologized for proposing something he feared could never be detected. He had invented the neutrino on paper, purely to save the books, and he doubted anyone would ever catch one. He was nearly right about how hard it would be. It took more than 2 decades before anyone managed to detect a neutrino directly, and it required sitting beside a nuclear reactor, which pours out these particles in floods, and watching for the vanishingly rare occasion when one deigned to interact. When it was finally done, in the 1950s, it confirmed that Pauli's desperate remedy was a real particle after all, and a staggeringly common one. We now know that neutrinos are among the most numerous particles in the universe, that the sun produces them in unfathomable numbers every second, and that when a distant star exploded in 1987, we caught a handful of the neutrinos it flung out, arriving at our detectors slightly ahead of the light, the first time we had ever felt a particle messenger from a dying star. Every step of that history was a lesson in the same strange truth. The neutrino is everywhere, it is essential, and it is almost impossible to touch. Which is exactly why, when the universe made a background of them in its first second, that background could survive, untouched, all the way to now. Let me slow all the way down here, because I want you to actually experience this rather than just be told it. Lie still for a moment and lift one hand into the dark above you. Hold it there, open, palm up, fingers loose. Now understand what is happening to it this second without any sensation at all. Through the skin of that palm, through the small bones and the blood and the warmth of it, neutrinos are passing. Not a few, trillions of them are crossing your hand every second, a silent flood pouring through the flesh as though it were open air. And a portion of that flood, a real and countable portion, are these ancient ones, the relic neutrinos, particles that stopped touching the rest of the universe when the cosmos was 1 second old, when there were no atoms, no stars, no galaxies, nothing but the cooling fire. They have crossed nearly 14 billion years and the entire width of the observable universe to arrive, and they are moving through your open hand right now, and not one of them touches a single atom of you. They do not warm your skin, they do not press on your palm, they give no sign. You could hold your hand up for the rest of your life and never feel one, and the whole time the oldest surviving things in existence would be streaming through your fingers, silent, constant, older than light, and utterly indifferent to the fact that you're there at all. Sit with that, because it is the truest strange thing I can offer you tonight. Something older than the first atom is inside your body at this moment, and has been every moment of your life, and will be every moment after. The beginning of the universe is not a closed door far behind you. It is passing through your open hand in the dark, and it has never once in all your years made contact. There is a certain grief in that, if you let yourself feel it, and also a certain intimacy. Grief, because the oldest thing there is moves through you and cannot be touched, a fossil you can hold your hand around and never hold. An intimacy, because it means you are not, after all, cut off from the origin. You are steeped in it. You're standing in a shower of the beginning, always have been, and the only reason it does not feel miraculous is that it makes no sound and leaves no mark. We are, of course, trying very hard to make contact anyway. There is an experiment called Ptolemy, whose entire purpose is to catch one of these relic neutrinos, just one, in the act. The method is exquisitely delicate. You take a form of hydrogen called tritium, which naturally decays and spits out an electron, and you watch those electrons with tremendous precision. Very rarely, the idea goes, instead of merely decaying, a tritium nucleus will actually capture a passing relic neutrino, and when it does, the electron it releases will come out with just a little more energy than a plain decay could ever give it, appearing as a tiny bump just past the normal limit, a signature that ordinary radioactivity cannot fake. If we ever see that bump, we will have directly touched the oldest surviving thing in the universe, read a message from the first second with our own instruments. As of now, we have not managed it. The signal is at the very edge of what is possible. But the fact that serious people are building machines to catch a particle older than light tells you something about how real these relics are. We are not speculating that they exist. We are trying to hold one. Think about what catching one would actually mean, because it is worth the effort we are pouring into it. The oldest light shows us the universe at 380,000 years, and it has already told us extraordinary things. But the relic neutrinos carry a snapshot from the universe at 1 second old, a window into an era we have never directly observed, only reconstructed. To detect them would be to confirm with a direct measurement that our understanding of that first second is correct, that the universe really did behave as our equations say when it was younger than a single heartbeat. And it would be more than a confirmation. Any surprise in that ancient neutrino background, any way it differed from the prediction, would be a message about physics we do not yet know, written into the universe before it was 2 seconds old. This is why serious people spend careers on an experiment that might, if everything works perfectly, catch a handful of particles a year. They are not chasing a curiosity. They are trying to read the oldest surviving text in existence in a language of particles that will barely stop to be read. And yet, as old as these neutrinos are, they are not the oldest possible relic, and they are not the central object of tonight's story. They decoupled at 1 second. But the universe was making things before 1 second. It was making things in the first fraction of the first second, before there were even protons and neutrons, before there was anything you would call ordinary matter at all. And one of those things, if it exists, would not be a ghost you cannot touch. It would be an object, a place, something with a location and a mass and, in principle, a surface you could fall toward. To reach it, we have to go back further than the neutrinos, into the first instant before matter itself. That is where we're going now. Part 6. Before matter itself. We have to be precise now about a phrase I've used several times because everything ahead depends on it. I keep saying before ordinary matter existed, and that can sound like loose language, a bit of drama. It is not. There is a specific, well-understood sequence of events in the early universe, a schedule of when each kind of thing first came to be, and ordinary matter has a definite place on that schedule. It did not exist at the start. It had to be assembled in stages, and understanding those stages is the key that unlocks the central object of tonight's story. Let me lay the schedule out, from the first instant forward, so you can see exactly when the familiar stuff of your body first appeared. At the very beginning, in the inflationary phase and the reheating that lit the fire, there was energy, radiation, and a churning bath of the most fundamental particles, but nothing you would recognize. There were no atoms, obviously. There were not even the pieces of atoms as you know them. The protons and neutrons that make up every nucleus in your body did not yet exist as protons and neutrons. Their ingredients, particles called quarks, were there, but they were not yet bound together into anything. They roamed free in a state so hot and dense that no combination could hold. The first great assembly happened at about 1/1,000,000th of a second. To write it properly, around 10 to the -6th of a second after the beginning. That is when the universe had cooled just enough for the quarks to bind together, 3 at a time, into the protons and neutrons we know. This event has a name, the quark-hadron transition, and it is the moment ordinary matter, in the most basic sense, first came into being. Before 1/1,000,000th of a second, there were no protons anywhere in existence. After it, the building blocks of every atom you contain were finally real. But protons and neutrons are not yet atoms, and they are not yet elements. The next assembly, the forging of the first atomic nuclei, when protons and neutrons fused into the lightest elements, hydrogen and helium, did not happen until the universe was about 3 minutes old. And the final assembly, the one where those nuclei captured electrons to become complete neutral atoms, is the very event we already visited, the clearing of the fog at 380,000 years when the oldest light was set free. So look at the schedule as a whole. Complete atoms at 380,000 years, atomic nuclei at 3 minutes, protons and neutrons, the first ordinary matter, at 1/1,000,000th of a second. Everything you are made of has a birthday, and none of those birthdays is the beginning. The universe ran and did things and made things in the long stretch of time before 1/1,000,000th of a second, when there was not yet a single proton anywhere in reality. And that is the door. Because here is the question that the central object of tonight's story is built on. If something formed before 1/1,000,000th of a second, before the first protons, then it was forged before ordinary matter existed, in the most exact and literal sense the words can carry. It would not be made of atoms because there were no atoms. It would not be made of protons because there were no protons. It would be made of whatever the universe was in that first instant, raw density, raw energy, folded up in a way that could survive. Is such a thing possible? Could the universe, in its first fraction of a second, before it had assembled a single piece of ordinary matter, have made an object that is still here today? The answer that a growing number of physicists give is yes, and the object has a name, and we are about to spend the rest of the night with it. There is one more thing worth understanding about that first assembly of ordinary matter, because it deepens how improbable your existence actually is. When the quarks bound together into protons and neutrons at 1/1,000,000th of a second, they did so out of a churning bath in which matter and its mirror opposite, antimatter, were being created in nearly equal amounts. And matter and antimatter, when they meet, annihilate each other completely, converting themselves entirely into radiation. So in that first instant, almost all the matter that existed was paired with an equal partner of antimatter, and almost all of it destroyed itself, matter and antimatter cancelling each other out across the whole young universe in a storm of light. If the balance had been perfect, there would be nothing left. No protons, no atoms, no galaxies, no you, only a universe of radiation and empty space. But the balance was not quite perfect. For reasons we still do not fully understand, there was a tiny surplus of matter over antimatter, something like one extra particle of matter for every billion matched pairs. When the Great Annihilation finished, that 1 in a billion surplus was all that survived. Everything you see, every star, every world, every atom of your body is built from that faint leftover, the tiny imbalance that escaped the mutual destruction. Ordinary matter is itself a kind of relic, the small remainder of a cancellation that very nearly erased everything. Keep that in mind as we go forward, because it sharpens the contrast. Ordinary matter barely survived, and only as a faint surplus, and it did not even take its familiar form until a millionth of a second had passed. But the object we are about to hunt did not need to wait for that surplus, and did not need protons, and did not need the annihilation to leave anything behind. It could form directly, from the raw density of the fire, in the instant before any of that bookkeeping was settled. It is, in every sense, more primordial than the matter you're made of. But before we name it and study it, I want to take you into that first instant and let you feel the conditions, because the object we are hunting was born there, and you cannot understand it without standing for a moment in the fire that made it. Close your eyes, if they are not closed already, and let me place you in the universe when it is far younger than a second old. There is no up and no down here, no sky, no ground, no room, no distance in any sense you know. There is only substance, everywhere, in every direction, without edge or gap. It is not a gas and not a liquid and not a solid. It is a state that has no everyday name, a searing, seamless density of energy, and the most fundamental particles, packed so tightly and moving so fast that the very idea of a separate individual thing has no meaning. Everything is touching everything. The temperature is beyond anything the word hot can hold, trillions upon trillions of degrees, so extreme that particles are being born and destroyed continuously out of the raw energy of the place, flickering into being and gone again faster than any clock could mark. This is not chaos exactly, because it obeys laws, but it is a ferocity with no still point anywhere in it, a boiling that fills all of existence because it is all of existence. And now notice something, because this is the whole point. This boiling is not perfectly even. It cannot be, because the flickers frozen in by inflation left it faintly uneven. A little denser here, a little thinner there, ripples of more and less laid down across the whole of it. Follow one of the denser spots. In most places, the pressure of all that furious energy pushes outward hard enough to resist collapse, and the dense spot simply smooths back into the churn. But imagine a spot dense enough, just dense enough, that its own gravity wins. Its weight begins to pull inward faster than the pressure can push back. It folds in on itself tighter and tighter, a pocket of the primordial fire collapsing under its own density, until it crosses the threshold where gravity seals it off from everything around it, wrapping it in a one-way surface, closing it into a black hole. Not from a star. There are no stars, will be no stars for 100 million years. This black hole is made straight from the raw density of the first instant, before the first proton, before ordinary matter, out of the fire itself. Open your eyes. That object, if it truly formed, did not evaporate back into the churn. It sealed itself away, and it carried the first instant forward, intact, across the entire age of the universe. It would be older than every proton in your body. It would be older than the oldest light. It would be, in the most rigorous sense available, a piece of the beginning that never left. It has a name. We call it a primordial black hole, and everything so far has only been the walk up to its door. Now we open it. Part 7. The object forged before matter. A primordial black hole is a simple idea with staggering consequences, so let me state it plainly before we explore it. It is a black hole that did not come from a star. It came from the early universe itself, from a pocket of the primordial density collapsing directly under its own gravity in the first fraction of a second. That is the whole definition. But every word of it pulls against what you probably believe about black holes, so we have to take it carefully. Almost everything you have heard about black holes concerns the kind that form when a massive star dies. A giant star runs out of fuel, its core collapses, and if it is heavy enough, nothing can stop the collapse, and a black hole is born from the ruin. Those are stellar black holes, and they are real, and we have found many of them. But notice the requirement buried in that story. You need a star first. You need the star to live and die, which takes millions of years, and before that you need the gas cloud that formed the star, and before that you need the universe to have cooled and structured enough to make gas clouds at all. Stellar black holes cannot exist until the universe is already old enough to have grown and killed a generation of giant stars, which is hundreds of millions of years into the story. They are latecomers. Primordial black holes are the opposite. They do not wait for stars because they do not need matter to be organized into stars or into anything. They need only the raw density of the early universe and a pocket of it dense enough to collapse. And that condition, if it was ever met, was met in the first instant, before there were protons, before ordinary matter, when the whole universe was the churning fire we stood inside a moment ago. This is why a primordial black hole would be the oldest object in existence. It would predate every proton. It would predate the oldest light by hundreds of thousands of years. It would be a sealed pocket of the first fraction of the first second, carried forward, untouched, to now. You might ask how a pocket of density becomes a black hole, and the answer is beautifully indifferent to what the pocket is made of. Gravity does not care whether it is pulling on protons or stars or pure energy. It cares only about how much energy is packed into how small a space. If you concentrate enough of anything into a small enough volume, gravity wins, and a black hole forms, and it no longer matters what went in. In the early universe, the concentration was already almost high enough everywhere. It would have taken only a modestly denser patch, a ripple slightly stronger than its neighbours, to tip that patch over the edge into collapse. Whether such patches existed and how many depends on the exact character of the ripple's inflation left behind, and that is a question we are still working to answer. But the mechanism is not exotic. It is the same gravity that holds you to your bed, applied to the densest conditions there have ever been. I should be honest with you about the uncertainty here, because it is a real part of the science, and not a flaw to hide. We do not know whether primordial black holes exist. We know they can exist, in the sense that the physics permits them, and the early universe had the raw conditions. But whether the first instant actually made any, and how many, and of what masses, depends on the fine details of those inflationary ripples, and those details are exactly what we are still trying to pin down. If the ripples were smooth and gentle everywhere, then no patch was ever dense enough to collapse, and there are no primordial black holes at all. If the ripples had occasional sharp peaks, rare spots far denser than the average, then those peaks could have tipped into black holes while the rest of the universe sailed on. So the existence of these objects is tied directly to a question about the texture of the very first instant, the statistics of its unevenness, and that is a question at the frontier of what we can currently calculate and measure. This is why you will hear physicists speak of primordial black holes with such care, saying could and might and may rather than are. The objects are permitted, motivated and testable, but not yet confirmed. That is the honest state of it. But notice that even this uncertainty is a kind of gift, because it means the question is live and answerable, and being actively pursued rather than closed. And notice too that the stakes of the answer are enormous, which is why so many careful people are chasing it. Now here is where the primordial black hole stops being a curiosity and becomes, possibly, one of the most important objects in the universe. Because if these things formed in any real number, they would still be here, and they would have mass, and mass has gravity, and gravity is exactly the thing the universe has too much of and cannot explain. Let me set that puzzle up properly, because it is the reason serious physicists spend their careers on primordial black holes. When we weigh galaxies, we do it by watching how they spin and how they move, and using the fact that gravity holds them together. And every time we do this, we get the same impossible answer. Galaxies contain far more gravity than their visible matter can account for. The stars and gas we can see are not nearly enough to hold a galaxy together at the speeds it spins. There should be 5 or 6 times more matter than we can see, an unseen mass wrapped around and through every galaxy, holding it together and yet giving off no light, absorbing no light, invisible to every telescope ever built. We call this unseen mass dark matter, and it is not a minor footnote. It outweighs all the visible matter in the universe by about 5 to 1. When you look up at the night sky and see all the stars and all the galaxies, you are seeing roughly the lesser portion of the matter that is actually there. The greater portion is dark, and we do not know what it is. The evidence for this invisible mass did not arrive all at once, and it is worth knowing how it built up, because it is the reason no serious scientist can simply wave the problem away. The first hint came in the 1930s, when an astronomer studying a great cluster of galaxies measured how fast those galaxies were moving around one another and found they were moving far too fast. At those speeds, the cluster should have flown apart long ago, its galaxies scattering into the void, unless something unseen was holding it together with extra gravity. He called this missing something the dark matter, and for a long time his result was treated as a curiosity, perhaps a mistake. Then, in the 1970s, an astronomer named Vera Rubin measured how individual galaxies spin, tracking how fast the stars at their edges circle the centre. By every expectation, stars far out at the rim, where the visible matter thins to almost nothing, should move slowly, the way the outer planets orbit the Sun far more slowly than the inner ones. Instead, she found the outer stars moving just as fast as the inner ones, as though the galaxy were embedded in a much larger invisible ball of mass, extending far beyond its glowing disk. Galaxy after galaxy told the same story. The visible spiral was only the bright core of something much larger and entirely dark. The most vivid demonstration came later still, from a collision. When two galaxy clusters smash through each other, the visible gas, the ordinary matter, drags and piles up in the middle, slowed by the collision. But by carefully measuring how the combined gravity bends the light of more distant galaxies behind the wreck, astronomers found that most of the mass had sailed straight through the collision and kept going, separating cleanly from the visible gas left behind. The gravity and the glowing matter had come apart. Something massive and invisible had passed through the crash almost untouched, exactly as a cloud of weakly interacting dark matter should. This was as close to seeing the invisible as we have come, watching where the mass was by the way it bent distant light, and finding it was not where the visible matter was. After all of that, the conclusion is no longer really in doubt. Most of the matter in the universe is dark. The only open question is what it is made of. For decades, the leading guess was that dark matter is some new kind of particle, one we have not yet discovered, filling space in invisible clouds. Enormous, careful experiments were built to catch these particles, sensitive detectors buried far underground to shield them from noise, waiting for a single unmistakable touch. And after decades of searching, those experiments have found nothing. The particles have not shown up. That failure is not proof they do not exist, but it has been long enough and thorough enough that people have begun, seriously, to ask whether dark matter might not be a new particle at all, whether it might be something we already understand, made in a form we did not expect. And this is where the primordial black hole steps into the centre of the stage. Because a primordial black hole requires no new particle, it requires nothing we do not already know exists. It needs only gravity, which we understand, and the early universe, which we know happened. If the first instant made enough of them, in the right range of masses, then the dark matter holding every galaxy together, the invisible 5/6 of all matter, could simply be a population of black holes older than the atoms, scattered through space, giving off no light because black holes give off no light, invisible for the most ordinary reason there is. The thing that lets galaxies exist, the unseen scaffolding that keeps the stars from flying apart, might be relics of the first fraction of a second. I want you to hold that idea still for a moment, because it is one of the most quietly astonishing thoughts in all of physics, and it is worth feeling and not just noting. Look up, in your mind, at the night sky, at the great wheel of the galaxy, at the fact that the stars are gathered into these enormous, stable, luminous islands, instead of scattered thin and cold across an empty void. That gathering, that structure, that the universe has galaxies at all, may rest entirely on a hidden mass, and that hidden mass may be a swarm of ancient black holes, forged before the first proton, threaded invisibly through and around every galaxy, holding it together with their gravity across all of time. The sky is not held up by the things that shine. The things that shine are held up by the things that are older than shining, older than matter, sealed pockets of the beginning that never announced themselves and never left. Every galaxy you have ever seen a picture of may be a gradient skin stretched over a skeleton of relics from the first instant. The visible universe may be resting quietly on the invisible bones of its own origin. Whether this is actually true is one of the great open questions in physics right now, and the honest answer is that we do not yet know. But we do know something crucial, and it keeps the idea very much alive. There is a particular range of masses in which primordial black holes could still be all of the dark matter, and no observation has been able to rule it out. Physicists call it the asteroid mass window. These would be black holes with the mass of a large asteroid or a small mountain, somewhere in the range of 10 to the 17th up to 10 to the 23rd grams, but compressed, because they are black holes, to sizes almost unimaginably small. A black hole with the mass of a mountain would be smaller than a single atom. It would be a speck of pure gravity, invisible, drifting, weighing as much as a mountain and yet finer than dust, and there could be enough of them, spread through space, to be the entire dark matter of the cosmos. That window has been squeezed from both sides by clever observations. Astronomers have used the precise tracked motions of the planets and spacecraft in our own solar system to look for the tiny gravitational tugs that a passing black hole would cause, and the absence of those tugs has ruled out part of the range. Others have proposed that such black holes drifting through solid bodies would leave strange marks, unlike ordinary impact craters, and searched for those. And still, the window has not closed. In the range around the mass of a mountain, primordial black holes remain a fully viable candidate for every bit of the dark matter in the universe. The unseen mass that holds the galaxies together could, as far as anyone has been able to prove otherwise, be a population of objects older than matter itself. So the primordial black hole is no longer just a strange possibility. It is a leading answer to one of the biggest questions in science, the question of what most of the universe is made of. And it hands us something the neutrino could not. The neutrino is a ghost, a fossil you can hold your hand around and never hold. But a primordial black hole is an object. It has a location. It has a mass. It has, in the most literal sense, a place. And if one is out there, then unlike the neutrino, it is at least conceivable that we could find it, mark it, point at a spot in the dark and say, there, that is a piece of the beginning, and it is right there. Step back for a moment and notice how much this single idea accomplishes at once, because that is what makes it so compelling to physicists. A primordial black hole would be, in one object, the oldest thing in existence, forged before matter in the first fraction of a second, and also a candidate answer to what most of the universe is made of, the dark matter that has eluded every other search. Those are two of the largest open questions in all of science, the nature of the beginning and the nature of the unseen majority of matter, and the primordial black hole reaches into both with the same hand. It requires no new particle, no undiscovered force, nothing beyond gravity and the early universe we already have strong evidence for. That economy is part of why the idea keeps returning, again and again, whenever the particle searches come up empty. A single kind of object made in the first instant could quietly hold two of the deepest puzzles together. Whether nature actually took that option is the open question. But the elegance of it is undeniable, and elegance in physics is often where the truth turns out to be hiding. But there is a complication, and it is a strange and haunting one, and it means that not all of these ancient objects are still with us. Some of them have been slowly dying this whole time. Black holes, it turns out, are not truly eternal. They leak, and the smallest, oldest ones may be reaching the very end of their long lives at this exact moment in cosmic history, ending in a flash after nearly 14 billion years of quietly bleeding away. To understand which primordial black holes are still here and which are vanishing tonight, we have to understand the slow, strange way a black hole dies. That is where we go next. Part 8. The ones that are dying right now. For most of the history of the idea, everyone assumed a black hole was forever. It only takes in and never gives back. Nothing escapes it. Not light, not matter, not information. So once something is a black hole, it can only grow or stay the same. It seemed as close to eternal as anything in physics. And then, in the 1970s, that assumption was overturned by one of the most surprising results in modern science, and the consequence for our primordial black holes is direct and personal. They have not all survived. Some are dying as we speak. The discovery is that black holes are not perfectly black. They glow, very faintly. And in glowing they lose mass, and in losing mass they slowly evaporate. The glow comes from the strange behavior of empty space at the very edge of a black hole, at the one-way surface we call the horizon. Empty space, it turns out, is not truly empty. At the smallest scales, it seethes with pairs of particles flickering into being and vanishing again, borrowed briefly from nothing and paid back an instant later. This is ordinary physics, well tested, happening everywhere, including right at the edge of a black hole. And at that edge, occasionally, one member of a pair falls in while the other escapes. The one that escapes carries away a tiny bit of energy, and to balance the books, the black hole must give up a matching tiny bit of its own mass. Particle by particle, across enormous spans of time, the black hole radiates itself away. We call this glow Hawking radiation, after the physicist who worked it out, and it means that a black hole, left alone, will very slowly shrink and eventually vanish. Now, for the giant black holes, the ones at the centres of galaxies weighing millions or billions of times the mass of the Sun, this process is so absurdly slow that it might as well not exist. Their lifetimes stretch to numbers with 100 zeros, so far beyond the current age of the universe that they are, for all practical purposes, immortal. But the rate of this evaporation depends fiercely on the mass, and here is the crucial and counterintuitive part. Small black holes are hotter and evaporate faster than large ones. The less massive a black hole is, the more furiously it glows and the quicker it dies. A black hole is that rare thing that gets hotter as it shrinks, and so its dying accelerates faster and faster, hotter and hotter, as it approaches the very end. The relationship is sharp. The lifetime of a black hole grows with the cube of its mass. Make it 10 times heavier, and it lasts 1,000 times longer. Make it 10 times lighter, and it dies 1,000 times sooner. And this simple rule, combined with the age of the universe, gives us a genuinely eerie result, one worth stating slowly. There is a specific mass, and it is not enormous. It is about the mass of a small mountain, roughly 170 billion kilograms, packed into a black hole finer than a single atom. A primordial black hole born with exactly that mass at the beginning of the universe would have a lifetime of almost exactly 13.8 billion years, and 13.8 billion years is the current age of the universe, which means the primordial black holes that were born with that particular mass are not dying in some far future, and they did not die in the distant past. They are reaching the end of their lives right now, in our cosmic era, at this point in the history of everything. Somewhere out in the dark, a black hole as old as time, one that has been quietly bleeding away for the entire age of the universe, is coming to the end of that long death this year, this night, and finishing in a burst. Let me take you to one, because a fact like this should be witnessed, not just stated. Somewhere in the dark between the stars an object is finishing. It formed in the first fraction of the first second, a pocket of the primordial fire sealed off before the first proton existed, and it has spent 13.8 billion years, the entire age of the universe, slowly leaking itself away, one faint particle at a time, so gradually that for almost all of that immense span it seemed to do nothing at all. It is smaller than an atom, and it weighs, still, something like a mountain, though far less than it once did. And now, in its final stretch, the slow leak becomes a torrent. As it sheds the last of its mass, it grows hotter, and the hotter it grows, the faster it sheds, and the faster it sheds, the hotter it grows, a runaway with no break at the end of it. In its last second it blazes, pouring out radiation at a rate that has been building toward this instant for 14 billion years, and then, in a final flash of high-energy light, a burst of gamma rays flung out into the dark, it is gone. Completely gone. A thing older than every atom, older than the oldest light, a sealed piece of the beginning that outlasted stars and galaxies, ends in an instant tonight, unseen, in the cold between the stars. The beginning of the universe is still, quietly, going off, like a last few embers of a fire that was lit before there was anything to burn. It is worth understanding just how strange and unexpected this dying is, because when it was first proposed it startled the physicist who found it as much as anyone. In the early 1970s, working through the mathematics of how the smallest scales of reality behave near the edge of a black hole, he arrived at a result he did not believe at first and checked and rechecked, because it seemed to contradict the very definition of a black hole. A black hole was supposed to be the one object from which nothing could ever escape, and yet the mathematics insisted that, seen from far away, a black hole must glow, must give off a faint thermal radiation, and must therefore slowly lose mass and eventually die. The result was so surprising that it took time for the community to accept it, but it has stood ever since as one of the deepest bridges we have between gravity and the physics of the very small, and it carries a strange consequence about temperature that is worth stating plainly. The temperature of a black hole runs opposite to its size. The bigger it is, the colder. The great black holes at the centres of galaxies are so cold that their temperature is a tiny fraction of a degree above absolute zero, colder even than the ancient background light that fills all of space. And that leads to a curious fact. Those giant black holes cannot even begin to truly evaporate yet, because they are colder than their surroundings, and so they absorb more warmth from the faint background light than they give off. They will only start to shrink in the far future, once the universe has expanded and cooled even further, long after the last stars have died. But run the logic the other way, down to the tiny primordial black holes, and the temperature climbs ferociously. A black hole the mass of a mountain, finer than an atom, is blisteringly hot in this sense, radiating hard, dying fast, and getting hotter as it goes. The smallest, oldest black holes are the ones burning themselves out now, precisely because being small means being hot, and being hot means being brief. There is something almost unbearably poignant in that image, and also something useful, because a flash is a thing we can look for. If small primordial black holes are ending their lives now, then their final bursts of gamma rays are a signal, a specific kind of high-energy flash with a specific rising signature, and we have telescopes that watch the sky for exactly such flashes. To catch one would be to witness the death of something as old as time, to see the last light of the first instant, and a detection would settle something that has haunted physics for half a century. The faint glow that makes black holes die has never once been directly observed. It was worked out on paper, and the reasoning is trusted, and it sits at the foundation of how we think gravity and the quantum world fit together. But no one has ever actually seen a black hole radiate, because for every black hole we know of, the glow is far too cold and faint to detect. A primordial black hole ending its life in a final burst would be the exception, the one place in the universe where that glow becomes bright enough to catch. To see one evaporate would be to confirm at last, with a real signal from the sky, an idea that has shaped physics for 50 years on the strength of mathematics alone. It would be the death of the oldest object in existence, delivering proof of one of our deepest theories in the same instant. Few observations could do so much at once. We have not confirmed such a detection, but the search is real, and the fact that we can even define what to look for tells you how concrete this has become. The oldest objects in existence may be announcing their deaths across the sky, and we are learning how to listen. But now step back and take the full measure of what this evaporation means for our hunt, because it cuts both ways, and the second way is the one that keeps the whole story alive. Yes, the small primordial black holes are dying, the mountain mass ones ending now, the lighter ones already long gone, evaporated in the distant past when the universe was young. But remember the cube law. Lifetime grows with the cube of mass, brutally fast. Go up only modestly in mass, to the asteroid mass window we spoke of, the black holes with the mass of a large asteroid rather than a small mountain, and their lifetimes do not merely double or triple. They soar to hundreds, thousands, millions of times the current age of the universe. Those black holes are not dying now. They will not die for an almost incomprehensible stretch of time. On any human or even cosmic scale, they are effectively immortal. They were forged before matter, and they are still here, whole, and they will remain whole long after the last star has burned out. So the evaporation does not empty the universe of its oldest objects. It sorts them. It removed the lightest ones long ago. It is removing the mountain mass ones in a scattering of gamma ray flashes right now, and it leaves the asteroid mass ones intact, drifting, patient, the survivors of the survivors. And those are precisely the ones that could be the dark matter. Those are the ones that could be threaded through every galaxy. And those are the ones that raise the most startling possibility of all, the one that turns this entire abstract story into something you could, in principle, point a spacecraft at. Because if primordial black holes of that mass are real, and if they are as common as the dark matter would require, then the odds are not negligible that one of them is close, not at the edge of the galaxy, close, possibly closer than you would ever dare to guess, possibly inside the reach of our own sun's family of worlds. That astonishing idea has an actual name and an actual scientific proposal behind it, and it is where we go next. Part 9. The one that might be next door. There is a mystery in our own solar system that has puzzled astronomers for more than a decade, and it opens the door to the strangest possibility in tonight's story, that the oldest object in existence might not be far away at all, but a member of our own sun's family, out in the cold past the last planet. To get there, we have to start with the mystery, because it is real and well documented, and only then follow it to the primordial black hole hiding at the end of it. Far beyond Neptune, in the frozen outer reaches of the solar system, there is a population of small icy worlds, and some of them behave oddly. A handful of the most distant ones, objects on enormous elongated orbits that carry them hundreds of times farther from the Sun than the Earth is, share a peculiar alignment. Their orbits are tilted and pointed in a way that looks coordinated, as though something were herding them, gently shepherding their paths into a pattern that random chance struggles to explain. When astronomers first noticed this clustering, the natural explanation was gravity. Something massive and unseen, far out in the dark, must be tugging on these distant worlds, sculpting their orbits from a distance, and so was born the idea of a ninth planet, an undiscovered world in the far outer solar system, several times the mass of the Earth, too dim and too distant to have been spotted, but making its presence felt through its gravity. This hypothetical world has been hunted for years. The astronomers who first argued for it refined their calculations, ran their simulations, and narrowed down where it ought to be and how heavy it ought to be. The current estimates put it at something like 5 to 10 times the mass of the Earth, orbiting at a tremendous distance, roughly 290 times as far from the Sun as our own planet, give or take. It is a serious mainstream idea, and many astronomers expect that if it exists, it will turn out to be an ordinary planet, a cold and distant world we simply have not managed to see yet. The search continues with the newest and most powerful survey telescopes, and it may be found any year now. But in 2019, two physicists asked a question that turned the whole thing on its head. They pointed out that the orbital clustering does not actually tell you what the unseen mass is. It only tells you that a certain amount of mass is out there, in a certain place, pulling. It tells you the gravity is present. It does not tell you what kind of object is producing that gravity. And a planet is not the only thing with the mass of several Earths. There is another kind of object with exactly that mass, an object that would be far, far smaller and far, far darker, and therefore far harder to find. A primordial black hole. Here is the astonishing arithmetic. If you take 5 to 10 times the mass of the Earth, and you ask how big a black hole of that mass would be, the answer is almost comically small. It would be roughly the size of a grapefruit size sphere of absolute darkness, weighing several times as much as the entire Earth, sitting in the cold 290 times farther from the Sun than we are. It would produce exactly the gravitational tug that the clustered orbits require because gravity depends only on mass, and its mass would be identical to the planet's. But it would give off no light of its own, and it would be so tiny that no ordinary search for a planet, looking for a faint reflective disk, would ever catch it. It would be, in the most literal way, hiding in plain darkness. The two physicists named Schultz and Unwin proposed exactly this, that the thing shepherding those distant orbits might not be a ninth planet at all, but a primordial black hole, captured by our Sun long ago, a relic of the first instant travelling with us through the galaxy. To feel the weight of this idea, it helps to know how the outer solar system mystery was found, because it was not invented to be exciting. It grew out of patient, almost tedious observation. Beginning in the early 2000s, astronomers surveying the sky for faint, slow-moving points of light began discovering small, icy worlds far beyond Neptune, in a region so cold and so distant that the Sun out there is little more than an unusually bright star. One of the first, discovered in 2003, followed such an enormous stretched orbit that it never came anywhere near the known planets, spending its entire long year in the far dark, which raised an immediate question, because nothing in the known solar system could have placed it on such a path. As more of these extreme distant worlds were found, a pattern emerged in the most careful analyses. Their stretched orbits were not pointed randomly in all directions as chance would predict. They leaned together, tilted and aligned, as though a common hand were tilting them the same way. In 2016, two astronomers argued that the cleanest explanation was an unseen massive body far beyond them, and worked out roughly how heavy it must be and where it must lie, and the modern hunt for a ninth planet began in earnest. Over the years since, those calculations have been refined and tested against new discoveries and better simulations. The estimated mass settled at several times that of the Earth, and the estimated distance at hundreds of times the Earth's distance from the Sun, out in a part of the solar system so remote and so dim that even our best telescopes could easily have missed a world of that size. The clustering that started it all has been debated, questioned, and re-examined, because with only a handful of distant worlds it's hard to be certain a pattern is real and not an accident of which ones we happen to find. But the mainstream conclusion has held up under scrutiny. Something out there, most likely, is doing the tilting. The only real argument is over what that something is. I need to be careful and honest here, because this is where the channel's promise to you matters most. This is a minority view. Most astronomers who study the outer solar system expect the ninth object, if it is real, to be an ordinary planet, and they have good reasons. But the black hole idea is not a fringe fantasy. It was proposed by serious physicists in a serious journal. It is mathematically consistent, and most importantly, it is testable. It makes predictions that we can go and check, and that testability is what lifts it out of speculation and makes it worth your attention tonight. Because think about what it would mean if it were true, and let me place you out there so you can feel it. Imagine standing at the edge of the solar system far past Neptune, so far that the sun is no longer a disk but only the brightest star in a sky full of them, giving almost no warmth, almost no light. It is dark here, and profoundly cold, and profoundly still. And in front of you, holding position against the field of distant stars, is an object the size of a grapefruit. You cannot see it. It emits nothing, reflects nothing. You know it is there only because of what it does to the light behind it. The stars directly beyond it are subtly bent, smeared, shifted from where they should be, their light curving around the little sphere of darkness as it passes, so that the object reveals itself as a small, wandering distortion in the star field, a place where the background is quietly wrong. And you understand, standing there, that this small dark thing weighs more than the entire Earth you were born on, and that it is older than the Earth by billions of years, older than the Sun, older than every atom in your body, a sealed pocket of the universe's first fraction of a second, forged before matter, and that it has been travelling with our Sun, quietly, through all of human history and all of history before that, out here in the cold, unseen, a piece of the beginning kept in our own solar system like a stone in a pocket we never knew we were carrying. The physics of that little sphere is worth dwelling on, because it is so unlike the planet it would be mistaken for. A planet of several Earth masses would be a huge world, thousands of miles across, with a surface you could in principle stand on. Compress that same mass into a black hole, and it becomes a point of darkness a few inches wide, its one-way surface, its horizon, no larger than a piece of fruit. Everything about it would be extreme close-up. Just above that tiny horizon, the pull of gravity would be so fierce and so sharply changing that anything falling in would be stretched into a thin stream long before it arrived, and the region right around it would be a place of violent physics. And yet step back even a modest distance, and all of that ferocity vanishes into ordinary gravity, the same gentle pull any body of that mass would exert, which is precisely why, from the distance of the inner solar system, it would betray itself only through the faint, patient tilting of far-off icy worlds. It is a thing that is savage at its surface and mild at arm's length, a few inches of the most extreme physics there is, wrapped in a wide, calm halo of perfectly normal gravity. That combination, tiny and dark and heavy and quiet, is exactly what would let a piece of the beginning hide in our own solar system for the entire history of humanity without once being seen. That is the vision, and whether or not it is true, we're going to find out, and soon, which is the remarkable part. A new observatory, an enormous survey telescope built to photograph the entire visible sky over and over with unprecedented sensitivity, is beginning its work. And physicists have pointed out that a black hole out there, even one giving off no light of its own, would not be perfectly quiet. Now and then, a small comet or a wisp of gas would fall toward it, and as that material spiraled in and was torn apart, it would flare, briefly, as its matter heated in the fall. A faint flash from a fixed point in the outer dark, appearing and fading, with no visible object at its centre. The new survey has a real chance of catching such a flare if it is there, which means that within the coming years we may actually learn whether the object shepherding those distant orbits is a cold ninth planet, or a grapefruit of darkness older than the sun. Sit with the size of that question. We may be on the verge of discovering that a relic of the universe's first instant has been orbiting our own sun the entire time, close enough that a future spacecraft, in principle, could be sent to study it. The oldest object in existence would not be a distant abstraction at the edge of the cosmos. It would be a neighbour. And the beginning of the universe, the thing we were told was sealed off forever behind 14 billion years, would turn out to be a member of our own solar family, waiting in the cold for us to notice it. Notice how the whole shape of this idea keeps returning to the same quiet reversal. We began the night assuming the oldest things must be the farthest away, out at the edge of the observable universe beyond any reach, and step by step the opposite has kept turning out to be true. The oldest particles are not at the edge, they are in your hand. The oldest objects are not only in distant galaxies, one may be a neighbour, out past the last planet travelling with our sun. The beginning, it seems, did not retreat to the horizon. It stayed close, threaded through the nearby dark, hidden not by distance but by darkness and by silence, waiting the whole time in places we had simply never thought to look. That reversal, that the most ancient things are also among the nearest, is the strange quiet gift at the centre of this entire subject. But primordial black holes and relic neutrinos, as ancient as they are, all formed after the fire lit, in the first second of the hot universe. There is one more relic to hunt, and it is the rarest and most precious of all, because it alone could carry a message from the other side of the fire, from the strange cold expansion that came before the furnace, from the true before. To find it, we have to learn to read the faintest possible tremor in the fabric of space. That is where we go now. Part 10. The signal from before the fire. Everything we have hunted so far, the relic neutrinos passing through your hand, the primordial black holes forged before matter, was made after the fire lit. They come from the first second of the hot universe, which is astonishingly early, but it is still after reheating, still after the furnace ignited. There is one more relic to look for, and it is different in kind from all the others, because it alone could carry information from the other side of the flame, from the strange cold expansion that came before the furnace. It is the faintest and most precious of all the survivors, and to understand it we have to think about what the fabric of space can remember. We tend to imagine space as a passive backdrop, an empty stage on which the events of the universe play out. But one of the great lessons of modern physics is that space is not a passive backdrop at all. It is a flexible thing. It can stretch, and it has stretched enormously throughout cosmic history. It can curve, and its curving is what we experience as gravity, and it can ripple. When masses move violently enough, they send waves through the fabric of space itself, actual stretching and squeezing of distance that travels outward at the speed of light. These are gravitational waves, and we have detected them from colliding black holes and merging neutron stars far across the universe, using instruments so sensitive they can measure a change in length smaller than the width of a proton across miles of laboratory. Space ripples, and we can now feel those ripples arrive. Now here is the idea that matters for tonight. If space can ripple, then the most violent event in all of history should have set it ringing. And there was no event more violent than inflation, the impossibly fast expansion that came before the fire. During inflation, the same quantum flickering that seeded the galaxies would also have sent waves through the fabric of space. Gravitational waves generated not by any object within the universe, but by the wild stretching of the universe itself. These would be primordial gravitational waves, and they are unlike every other relic because they were made during inflation, before reheating, before the furnace lit. They come from before the fire. They are the one possible messenger from the true before, the phase that preceded the hot Big Bang entirely. Think about how extraordinary that would be. The relic neutrinos show us the universe at 1 second old. The oldest light shows us 380,000 years. But primordial gravitational waves would carry the imprint of the inflationary instant 10 to the minus 30-something of a second. From before there was a fireball at all. They would be a signal from the epoch that the tidy old story said could not have a before. If we could read them, we would be holding the closest thing possible to a direct trace of the moment before the beginning, a tremor still passing through space, laid down before the universe was hot, before it was a furnace, when it was still the cold, impossible expansion. It is worth remembering how recently we learned to feel any gravitational waves at all, because it tells you both how hard the problem is and how fast we're moving. For a full century after these waves were first predicted, they remained purely theoretical, so faint that most physicists doubted we would ever measure one directly. The stretching and squeezing of space they cause is almost absurdly small. When a wave from a pair of colliding black holes far across the universe washes over the Earth, it changes the length of a several-mile-long instrument by less than the width of a single proton, a change so tiny it is like measuring the distance to the nearest star and detecting a shift the width of a hair. And yet in 2015, after decades of effort, two enormous instruments finally felt exactly that. The passing tremor of two black holes merging more than 1 billion years ago, arriving as a rising chirp in the machines. It was the first time humanity had ever directly felt a ripple in the fabric of space, and it opened an entirely new way of sensing the universe, not with light, but with the trembling of space itself. That we can now feel space ripple at all is the reason it is even thinkable to hunt for the oldest ripples of them all. So why have we not simply detected the primordial ones, the way we detected the waves from colliding black holes? Because these primordial waves are almost unimaginably faint. They have been stretched and diluted by the entire subsequent expansion of the universe, spread so thin across so much space that measuring them directly is far beyond any instrument we have. But there is an indirect way to look for them, and it is beautiful, and it ties back to the oldest light we already met. When a primordial gravitational wave passed through the young universe, it would have gently squeezed and stretched the hot plasma, and that squeezing would have left a faint, particular twist in the pattern of the oldest light, a subtle swirl in the way that light is polarized, a signature that nothing else could easily produce. Physicists call this swirl a B-mode pattern, and finding it in the oldest light would be indirect but powerful evidence that primordial gravitational waves are real, and that inflation happened, and that the fire truly had a before. This is one of the great hunts in cosmology right now. Teams have built specialized instruments, many of them at the South Pole where the air is thin and dry and still, staring at the oldest light with exquisite care, trying to tease out that faint swirl from all the other patterns and all the interfering dust. So far they have not found it. They have placed limits, ruling out the strongest versions, narrowing the possibilities, but the swirl itself, the fingerprint of the waves from before the fire, has not yet been caught. New experiments are being planned and built, including proposed satellites designed specifically to hunt this signal from above the atmosphere, with sensitivity far beyond what we have now. The search continues, patient and painstaking because the prize is almost beyond measure. To find that swirl would be to read a message from before the beginning of the universe as we usually define it. I want you to feel the shape of what we are reaching for here, because it is the ultimate version of the whole night's theme. We began with the tidy story, in which the beginning was a wall and nothing lay behind it. We found that the fire had a before, and now we are reaching out, with instruments at the bottom of the world, trying to catch a tremor that was set into the fabric of space during that before. A tremor that is still, right now, passing through everything, through the observatory, through the ice, through you, carrying the faintest possible memory of the instant before the furnace lit. We have not caught it yet. We may catch it in the coming years, and if we do, we will have done something that would have seemed like nonsense a century ago. We will have reached a hand past the beginning and touched what came before it. Notice what all of this is telling us about relics, taken together. Each one reaches back further than the last. The oldest light, from 380,000 years. The relic neutrinos from 1 second. The primordial black holes, from the first fraction of a second before matter. And the primordial gravitational waves, from before the fire itself, from the inflationary before. It is a series of survivors, each older than the previous, each a different kind of loophole in destruction, and each still here, still passing through the present, still available in principle to be measured. The beginning did not vanish. It layered. It left a nested set of traces, and we are slowly, patiently, learning to read each layer, working our way backward through the survivors toward the very first instant. And that is nearly the whole picture. But before we gather it all together and ask what it means, I owe you a promise the channel always keeps. When a subject touches the very origin of everything, it attracts not only careful science but also a great deal of fear and fantasy. Claims that the whole thing is faked, or that one of these ancient objects is a danger racing toward us. I do not want to leave those unaddressed, because the truth about them is calmer and stranger than the fear, and understanding why they are wrong will make what is actually true stand out all the more clearly. So before we close, let us sit for a while with what people fear about the beginning and what the evidence actually shows. That is where we go next. Part 11. what people fear, and what the evidence shows. Whenever a subject reaches all the way down to the origin of everything, it draws two kinds of attention. It draws careful science, the kind we have been doing all night, and it draws fear and fantasy and the particular thrill of believing that the experts have it all wrong. I want to spend some time here gently, with the fears, not to mock them, because some of them come from a very human place, but to hold each one up against the evidence and let you see calmly what actually holds together and what does not. And I think you will find, as we often do on this channel, that the truth is stranger and quieter than the fear, and in its own way more comforting. The first fear is the biggest one, and it is a kind of total suspicion. It says that none of this is real, that the distances are made up, that the early universe is a story, that the whole edifice of cosmology, the billions of years, the fireball, the expansion, is an elaborate fabrication, and that the sky might even be a kind of dome, a screen, a fake. It is worth taking this seriously enough to answer properly, because the answer reveals just how sturdy the real picture is. The distances we use are not a single measurement made by a single group that you would have to simply trust. They are built up in overlapping layers, each checked against the others. For nearby objects we use simple geometry, the same triangulation a surveyor uses, watching how a star appears to shift against the background as the Earth moves around the Sun. For objects in our own solar system, we bounce radar off them and time the return, measuring distance directly with the speed of light. For farther objects, we use stars and exploding stars whose true brightness we understand, so that how dim they appear tells us how far they are. And the remarkable thing, the thing that makes the fabrication story collapse, is that these completely independent methods agree with one another and hand off from one to the next seamlessly, and together weave a single consistent map. The temperature and pattern of the oldest light were predicted on paper before anyone measured them and then found to match. A fabrication does not make predictions that come true decades later from separate directions. The consistency across independent methods is exactly what a real picture looks like, and exactly what a faked one could not sustain. The second fear is more specific, and it attaches itself to the very thing that makes tonight's story so vivid, the primordial black hole in our solar system. Once you hear that there might be a black hole out past Neptune, the fear writes itself. A black hole, here, in our neighbourhood, must be a threat. It must be pulling us in, or coming for us, or waiting to swallow the Earth. So let me put that fear to rest carefully, because the reality is genuinely reassuring. If such an object exists, it sits at a tremendous distance, roughly 290 times as far from the Sun as we are, on a stable, distant orbit that it has held for billions of years. It is not approaching, it is not falling toward us. A black hole is not a cosmic vacuum cleaner with some special reach. Its gravity, at a given distance, is exactly the same as that of any object with the same mass. If you replace this hypothetical grapefruit-sized black hole with an ordinary planet of the same several Earth mass, at the same distance, its gravitational effect on us would be identical, and no one would fear an ordinary distant planet. The black hole is frightening only because of the word, not because of the physics. At that distance, with that mass, it is as harmless as any far-off world, and it has been harmlessly out there, if it is there at all, through the entire history of life on Earth. The third fear is subtler, and it comes from the very intimacy we spent so much of tonight on. If ancient neutrinos are pouring through my body, and if primordial black holes might be drifting through the solar system, am I being bombarded? Am I in some slow, invisible danger from all these relics passing through me? And the answer returns us to the beautiful reason these things are relics at all. They survive because they barely interact, and barely interacting means barely affecting you. The relic neutrinos pass through you precisely because they almost never touch anything, which is the same reason they cannot harm you. They slip through your atoms without disturbing a single one, and the primordial black holes of the asteroid mass range, even if one drifted through the solar system, are so small, finer than an atom, that the chance of one hitting you, or the Earth, in any meaningful way is vanishingly remote, and their passage would be a gravitational whisper, not a blow. The unsettling thing about these relics was never danger. It was intimacy. It was the strange fact that the oldest things in existence move through us and around us and leave no mark. That is not a threat. It is a kind of quiet companionship we simply never noticed. There is a fourth reaction worth addressing, gentler than the others but just as common, and it points in the opposite direction. It is not fear but a leap to certainty. When people learn that the universe had a beginning, that it emerged from a single hot instant preceded by an even stranger expansion, some feel that this must prove a grand design, a deliberate hand, a purpose written into the origin, and that scientists must be quietly hiding this obvious conclusion. I want to be careful and fair here, because this touches on things people hold close, and it is not my place to tell anyone what to believe about meaning or purpose. What I can tell you is only what the physics does and does not say. The physics describes how the early universe behaved, the expansion, the fire, the relics, in remarkable detail, and it genuinely does not reach a verdict on why there is something rather than nothing, or whether the whole arrangement means anything. Scientists are not hiding an answer to that question. They simply do not have one, and most are honest enough to say so. The beginning is a fact we can study. What it means, if it means anything, is a question that sits beyond the edge of what measurement can decide, and thoughtful people land in very different places on it. The science neither forecloses those answers nor supplies them. It only patiently describes the how, and that fairness matters, because it is the same even-handedness we owe the wilder scientific claims. We do not accept the primordial black hole because it is exciting, and we do not reject the faked universe story because it is unpleasant. We weigh each one against the evidence calmly and let the weighing decide. That habit, applied consistently, is the whole method, and it is what lets us say something true about the beginning of everything, without either fooling ourselves or frightening ourselves. Do you see the pattern in all of these? The fears in each case imagine the origin of the universe as something hostile, hidden, or hunting, and the evidence in each case shows something calmer and more remarkable. The distances are not faked. They are cross-checked from a dozen directions into a single sturdy map. The distant black hole, if it exists, is not coming for us. It is a quiet, ancient neighbour holding its orbit. The relics passing through you are not bombarding you. They are moving through you as gently as they have moved through everything for 14 billion years. The universe is not sneaking up on you. It is simply everywhere, ancient, and mostly indifferent, and the indifference is not cruelty. It is the reason any of this survived to reach you at all, and that, I think, is the quiet centre of why this channel keeps returning to the fringe theories only to set them gently down. The real universe does not need to be made scarier than it is. It is already stranger than the fears, and once you understand it, kinder than the fears. Something ancient really is here, really did survive from before the fire, really is passing through your open hand in the dark. It is not hunting you, it is just old and quiet and everywhere. And the fact that we can know that we can build instruments at the bottom of the world and telescopes that map the whole sky, and detectors that wait for a single ancient particle and actually learn the truth about the beginning of everything, is not a horror. It is one of the most astonishing things our small, warm, curious species has ever done, which brings us at last to what all of this means, and to the strange and beautiful thought I have been saving for the end. That is where we go now, slowly, to close. Part 12. Holding a fossil of the origin. We have travelled a long way tonight, from the tidy story with the clean floor to the survivors of the first instant, and now, gently, I want to gather it all together, and then I want to leave you with one thought to carry down into sleep. So let us walk back through what we have found, slowly, the way you might walk back through a house turning off the lights, one room at a time. We began with a comfortable story, the one that says the beginning was a single moment with nothing behind it, a universe with no attic and no keepsakes, and we found that the story was too small. We found, first, that the fire had a before, that the hot furnace we call the Big Bang was a second act, lit by the strange cold expansion of inflation that came before it, so that the word before is not forbidden after all. And we found, second, that a small and precious number of things made in those first moments never left. They survived the most hostile conditions that have ever existed, each by finding a different loophole in destruction, and they are still here, threaded through the present, available to be found. We met the oldest light, the afterglow of the fog clearing at 380,000 years, a baby photograph of the cosmos printed across the whole sky, and we learned that famous as it is not the oldest relic. We met the relic neutrinos, older than the light by hundreds of thousands of years, decoupled when the universe was 1 second old, 336 of them in every sugar cube of space, pouring through your open hand this very moment, trillions a second and never touching you, a fossil you can hold your hand around and never hold. We went back further, before matter itself, before the first proton, and found the primordial black holes, sealed pockets of the first instant, possibly the dark matter that holds every galaxy together, the invisible bones under the visible sky. We learned that the smallest of them are dying now, ending in flashes of ancient light out in the dark while the asteroid mass ones drift on, effectively immortal, the survivors of the survivors. We stood at the edge of our own solar system beside the possibility that one of them, a grapefruit of darkness older than the sun, has been travelling with us all along, close enough that we may soon catch its flare. And finally we reached out for the faintest relic of all, the primordial gravitational waves, the one messenger that could come from before the fire, a tremor still passing through space, carrying the memory of the instant before the beginning, which we have not yet caught but are straining, at the bottom of the world, to hear. Now let me draw the thread all the way tight, because here is the thought I have been saving. You are made of the fire. Every atom in your body was assembled after the beginning, forged in the furnace and in the stars that came later, the ash of an ancient burning. In that sense you are a latecomer, built from the second act, from the matter that did not exist in the first fraction of the first second. But drifting through you, this moment, and out past the last planet, and threaded invisibly through every galaxy in the sky, are the few things that came before even the ash. The neutrinos older than light, passing through your open hand. The black holes older than matter, holding the galaxies together and quietly dying in the dark. The tremor from before the fire still moving through the fabric of space. The beginning of the universe is not sealed away behind you. It is in the room. It is in your body. It never left. And here is the part that turns it, at the very end, from something cold into something I find almost unbearably moving. For nearly 14 billion years, these relics drifted through a universe that did not know they were there. The neutrinos poured through rock and water and empty space with nothing to notice them. The black holes shepherded orbits and held galaxies together with nothing to wonder at them. The tremor passed through the dark, unheard. And then, on one small warm world after all that time, something appeared that could look up and reason backward and realize that it was steeped in the survivors of the beginning. You, us. The part of the universe that finally turned around and noticed its own oldest pieces still moving through it. The relic and the mind that finds the relic are made of the same universe, meeting each other across the whole of time, in the dark, in this room, tonight. So as you lie there, and the night settles, and you begin to drift, I want you to hold one quiet thing. The oldest things in existence are not far away. They are not a story about long ago. They are here now, passing through your open hand, silent and constant and older than light. And they have been with you every moment of your life, and they will be with you every moment after. The beginning never ended. It never left. It is still here. And for one strange and lucky span, so are you, the small warm part of it that gets to know. There is a gentleness in this that I want to leave you with, rather than a chill. We often tell the story of the cosmos as a story of loss, of things ending, of stars burning out, and the universe running down toward a cold and empty future. And all of that is true, and we have told those stories on this channel before, slowly in the dark, and we will again. But tonight is the other half of that truth, the half we do not tell often enough. The universe does not only lose things, it keeps a few. Out of the most violent beginning imaginable, out of a fire that unmade almost everything it touched, a small number of things slipped through and endured, and they are still with us, and they are not going anywhere for an unthinkable span of time to come. The neutrinos will still be pouring through the space where the Earth used to be long after the sun has died. The asteroid mass black holes will still be drifting, whole, when the last star has gone dark. The tremor from before the fire will still be moving through space when there is no one left to listen. These are not things that are ending. These are the things that outlast endings. And for a very brief moment on the scale of all that time, there is you, lying here in the dark knowing about them. That is the part I keep coming back to. The relics have been here for 14 billion years, patient, silent, unremarked. And you have been here for a handful of decades, if you are lucky, a flicker against their immensity. and yet it is you, the flicker, who gets to hold the thought. It is the brief, warm, thinking thing that gets to know about the ancient, cold, enduring one. The universe made survivors of its own beginning, and then, after all that time, it made something that could notice. Both of those are astonishing. That they exist in the same moment in this room is the most astonishing thing of all. Rest now. The ancient things will keep drifting through the dark, the way they always have, whether we watch or not. But tonight, for a little while, you knew they were there. And that is a rare and beautiful thing for a piece of the universe to be able to say. Sleep well. They are still here. They always will be.